I wanted to ask you about algebraic effects by Gordon Plotkin, and later developed by Matthew Pretner, and I was also listening Andrew Bauer about. What is your like overview, if you can say, and the connection to for example, OSLF?
Yeah. So in general, an effect system is slightly different than what we're trying to do. So the effect system separates out types and effects. Let me just, I have not looked at the algebraic effects. Let me just quickly look at that.
In the lectures by Andrew Bauer, he introduced in the beginning this notion of monoid and like difference from a group, and this equational reasoning, and also equality. He was talking about three different equalities, and in a sense, I'm connecting this to your presentation about defining the language, like just by definition, something can be equal, and also when we reduce some terms, we can get to also something equal, but they are not completely the same, and they're representing this as different proofs, which somehow I'm connecting what you were saying, what you presented a few weeks ago, also that you can have different proofs that are basically for the same thing.
Yeah, but that's not quite what's going on here. So again, this is like if you follow John Weekly's answer to the difference between monads and algebraic effects, the idea that he puts forward, and again, I'm not sure if this is the consensus of the community, but the idea that he puts forward is that monads are essentially syntactic, and I tend to agree with that point of view, whereas the algebraic effects are effectively semantic. So he gives an example where you think of the state operations as like the operations on a cell, right? So you can get a state and you can put a state, and then you can interpret, what's going on with these states via some denotation map, right? And that's a decidedly semantic operation as opposed to a as opposed to a syntactic operation. So let me take a look and see if there's another view. Okay, let's see. Okay, well, that's a slightly different view, but it's less mathematical.
And I'm wondering if, I mean, they're saying this is compositional, and but
sure.
On the first sight, it's not, that doesn't look like.
So, okay, so Plotkin and Power are gaining popularity, blah, blah, blah. Okay. Interesting. Yeah, but it's This paper doesn't give, they give a lot of syntax, but they don't give an actual map. Okay, type scheme, constants. Well, I'd have to review the literature. I mean, types and effect systems have been around for a while, but I just want to make sure that when we're talking about algebraic effects, we're referring to the same things. I suppose I can look up, see what Plotkin's paper says. Plotkin algebraic effects. Let's take a look. Okay, well, here's a.
I was looking at one presentation as a summary.
Let me take a look here. Here we go. This looks like closer to the original paper. I'll just take a quick look. All right, so okay, so they don't have. I see. It looks relatively ad hoc, which is probably why the programming community jumped on it. So Plotkin and Power propose to represent effects by a set of operations that represent the source of effects and an equational theory for these operations that describe their properties. But what they're not saying is that, you know, there's any underlying order to that. So it could be any old set of operations and any old equational theory. You know, they're not saying that, for example, it has to be a Levier theory. It could be something more sophisticated than a Levier theory. So that's pretty Wild Westy. So I guess. Yeah, I'm not seeing it as anything other than. So let's see. Yeah, they have a language of signatures.
And for example, if in effect handlers, if this is just abstractions, like a function.
Yeah, exactly.
Then the question is, what kind of state is inside, and if this can like work concurrently, if we, because we are hiding some state inside some function, and I see this as a problem.
Yeah, I'm honestly not seeing a lot of structure here. It looks like the structure is fairly Wild West. Yeah. Where F is a what?
F, they created this F as a like example language.
No. I'm looking at one of Plotkin's later papers, 2009 paper. So they give a type language, but they don't say, but they use F, and F is unbound. I guess it must be a monad. Okay. Yeah, right. So they do. Yeah. So F is going to be some monad that freezes a computation. turns a computation into a value. Yeah, so they have binary products, index sums, and then they have typed indexed products for the computations and abstractions, things that take an A and produce a okay, yeah, this doesn't look particularly, I'm not sure why people feel that there's a lot of computational power here. I'm not seeing that as a particularly useful framework, especially in the presence of concurrency. It's hard to see whether or not given effects will step on each other's toes, unless that's what's guaranteed by the thunking. Yeah, yeah, that's particularly. So for example, here, let me do a screen share. All right, so here's from Plotkin's paper. So they have value types and computation types. So U turns a computation type into a value type.
This is like running the
I see.
computation.
U and F, so free and forgetful is why they're using U and F. So you have some set of base types. You have a unit for the product. You have a product. You have index sums, and you have the ability to turn a computation type into a value type. Here, you can turn a value type into a computation type, right? So these two are dual to each other. And then you have an index product, and then you have an abstraction which takes a value type and returns a computation. So there's going to be some kind of equation, or there ought to be, for purposes of sanity, you want to have some kind of equational relationship between this kind of abstraction and this, right? Because this is taking a value and producing a computation, and this is taking a value and producing a computation. So there needs to be some kind of relationship between these two. And then here's your term.
What's the difference between a computation type and a value type, or what are the differences of each?
So the metaphor that they're using are thunks, so freezing and thawing. A thunk in functional languages, a thunk is you wrap a lambda with an empty argument list around a value, and that's a computation type. And then, sorry, that's the other way around. I've got it backwards. So you have some computation type, you wrap it up in a lambda, so it's frozen, and then thawing it will give you back the computation. So this is thunking or freezing, and this is thawing. I don't know if you're familiar with this, but old schemers are familiar with this. Let me see if I can. Okay, so if we have, lambda, and now we don't give any arguments, so dot m, where m is some term. So m can't evaluate, right? It's stuck underneath this abstraction. So let me make this larger. Okay, that should be legible, right? So if we say thunk, or better, freeze m is defined to be, defined to be that, then thaw m, is defined to be apply m to no arguments, which is just that. So you see what will happen is m can't be evaluated because it's wrapped up in an abstraction that takes no arguments. And then when I call this lambda expression with no arguments, I'll start evaluating M. And that's the role. So U is freeze and F is thaw. Does that make sense?
Yeah. Okay.
Cool. So in a row calculus.
Can I ask one other question on this computational thing, computational type courses? So does this relate in any way to like lazy evaluation, or lazy evaluation is at a different level from this?
No, it's closely related to lazy evaluation. So
okay.
Yeah.
I'm thinking how the whole cat's effects are really based on the tongue.
Yeah.
Because this referential transparency is built from this suspension of execution.
Yeah, and now notice that in row, we have two different ways to achieve this, right? So I have P, which is a computation, and then I have at P, which is a name. So the computation is suspended when I send it.
And with star, we basically, we are like running.
Right, and then star X, right, which is going to be star of some at P is running. So this is like freeze and thaw. But you also have, for, you could say, I don't have any arguments, right? Or another way of doing that is that. Right, so that suspends P as well. But it suspends P at a location, right? So P is suspended at X as opposed to, so you see, Lambda is not aware of location except for textual side-by-sideness, whereas, Rho is aware of locations.
I see.
Yeah.
So they don't have. So basically, they're building this on lambda corpus, and
yeah,
they will need to add later some kind of
concurrency
way
mechanism.
to concurrency.
Yeah, exactly.
Because,
yeah. Yeah, that's why it's a little less interesting. It's also, I have a feeling that there's probably more to this. There's more underlying assumptions here. Yeah, so it's like you've got a category. It's got products. It's got co-products. And it's got some. What they've done is they've taken the monad and they've broken it up into an adjunction. That's what the U and the F are all about. So yeah. Yeah. So
this is like similar how now monics can work. Like we can have different implementation for execution, basically execution monad, right? And each flight map is a place where scheduler can change the thread and stop the execution.
Yeah, exactly. So you don't have like an explicit representation of your execution model, which is too abstract. It's not going to give you a lot of bang for buck, right? That's the thing that I think really needs to be understood is what's your bang for buck in terms of the formal model. And here it looks, so you've got products, you've got co-products. Well, this is interesting. You don't have full so it's not closed, right? It only goes from values to computations. So then you have to hit it with a U. But it's not clear how you would do that, actually. So if I get one of those, how do I whack it with a U?
Well, in the 2.3, they say, just the page below, they say they also have things called handler terms.
Yeah, no, but these are the terms. These are the types and these are the terms. So I guess what you could do is you could whack the outside with a U, but then how do you do an apply? That's not exactly clear. Yeah, that is not clear at all.
but at least they are presenting in this style. So I wanted to see how you compare, like different approaches, because some languages that don't have anything and they're just saying, whatever.
Well, again, category theory is really, really not a good fit for concurrency, because you either have tensor, which is isolation, or you have you don't have something like par, and to build something like par is a lot of work. I'm not particularly convinced by the various notions of various categorical attempts to model par. So you have to have you have to split par into the interaction part and the isolation part, and there's not a smooth way to get them to integrate. So that's one of the big open questions in categorical representations of concurrency theory. So you're going to have some kind of tensor, and you're going to have some adjoint to that tensor. Does that make sense? So you have some tensor product that's representing isolation, and you have some adjoint to that tensor, like a lollipop or a rely guarantee type. But it forces you into grouping things in a particular way. So my opinion is that you want an untyped language that has all your features, just like Lambda is untyped, and then you have a type system that you layer over top of that to guarantee some set of properties for your terms. But if the term formation doesn't allow for this kind of more loosey-goosey formulation of computations, then it's awfully strict, right? It says that you had to make all of your determinations up front rather than to have the type system check your work, so to speak. So yeah, this looks suspiciously like so if I suppose if I wanted to be generous, instead of having a product, I could insist on a tensor rather than a product, and then.
Okay, can you explain a little bit more? What do you mean by that?
So, the biggest difference between a tensor and a product is that the products have projections and tensors don't have projections. So they get, when you tensor things, you don't necessarily have a way of getting the terms back out. So we think of the tens. So product is obviously a monoid at the type level, right? So I can, if I have arbitrary products, then I can take two, tuples, and I can product them together, right, and get a new product, right? So and the unit always, the one element set, which is the one, is a unit for that, because I can always just project out and forget that particular component, because it's not really adding information. So that's clearly a monoid, but it's a monoid that has some extra information available. In particular, you have the ability to duplicate, right? So you have the ability to go from A to A cross A. So I can take a value and I can copy it. In a tensor, I don't have the projectors, and I also don't have the ability to copy.
Oh, so when you say projectors, you mean like first and second?
Yeah, exactly. That's right. So the tensor doesn't necessarily, it may be around, but it doesn't necessarily have the projectors, and it doesn't guarantee you a duplicator. But it's still a monoid, right, on the objects of the category.
I see.
So I suppose what you could do, and then I suppose you could have a cotensor, and I'd have to look up the relationship between tensors and cotensors, and when you have enough information that it collapses to products. But if you have a tensor, you have a cotensor, and then you have this adjunction that you split up, and then yes, so this looks like finite products, arbitrary coproducts. So I suppose you could do the same thing, but again, I don't know when all this extra stuff starts to collapse it back down to product. But you could have you could have finite tensor, arbitrary cotensor of values, and then you have arbitrary tensor of computations, and then you have this monad that's split into an adjunction. Yeah. Okay. So I think this thing could be generalized to a categorical situation where you do have some notion of concurrency, where the concurrency is a tensor and a cotensor, right? So the cotensor is yeah, that's interesting. So yeah, you'd have to play around with it a bit. So, but I have a feeling that it would be. Yes.
So basically, you're saying that this is a definition of how pieces of computation are structured, and we have a way to run it.
Yeah.
And with Rolling, we directly have
yeah, but see, the thing that's funny about this, the thing that's a little bit weird about this is, how do I say this? Like resumptions or continuations, they're really weird in a concurrency setting, right? Because, you could ask that you roll back state across a bunch of different threads, right? And so that starts to get really onerous, right? So imagine at internet scale, you can roll back all the state across all these threads, right? That's really weird, right? That starts to get computationally onerous. And so a lot of that computational, like limiting the scope of that has to do with the fact that you're essentially doing this in a lambda-like setting. I think as soon as you change this product to a tensor, and again, I have to think hard about the cotensor situation. But as soon as you change this product to a tensor, the ability to roll back becomes more restricted. In particular, you don't have a duplicator, and because you don't have a duplicator, you're going to be limited in terms of the kinds of rollbacks you can do. Yeah. So, but I think you could take this language and you could generalize it. It's an interesting it's an interesting construction. I mean, this is slightly more interesting than just some equations and some handlers. This says a lot more about it, about what you've got. So I mean, if this is the thing, then it's it pretty much implies lambda, which means it's like not so interesting.
Yeah, I'm thinking that how people who see something useful from this kind of stuff can also see even more looking at Rolling and all of the
yeah. I mean, with Rolling, yeah. So I think what's going to be super important is to have some kind of impedance match, impedance matching capability between Rolling and or between concurrency and the issue is that concurrency is just way more expressive. So so there's a mindset there's a flip that has to happen. And right now, people can think about threads, but they don't think about threads as syntactic entities. They think about threads as, orthogonal to the syntax, right? And that's what needs to be That's what needs to be, where people's minds have to be expanded a little bit, right? You know, imagining that you have a type constructor that will give you concurrency. So you can detect it syntactically.
I see.
Right.
Yeah.
I mean, that's ultimately the name of the game, is like, can you think about concurrency syntactically? Can you think about it at the type level? Can I catch this at the type level? Right. So you give me some code and I just look at the code in terms of its structure and I determine facts about the concurrency. Like with a piece of Java code, you can't do that, right? If I just write some arbitrary piece of Java code, you have no idea how many threads might pass through that, because I can place it in some context and lots of threads go through it, right?
Yeah.
So you can't look at the code and say what the concurrency characteristics are. With Rolang, you can look at the code and say, look, there's n different pars here. So there's, you know, n plus one threads.
Yeah, yeah.
So.
And I want to ask you also, you mentioned tensor and how you represented a graph language or language for graphs.
Yeah.
I found that there is some existing algebraic representation of graphs.
There are several proposals, and they all suffer from certain features.
And so I'm thinking there are like existing code and libraries, and I'm wondering what they're missing. Can for example, I think about some kind of modification and use some existing code.
So if you I've made this point so many times, but hang on, I'll show you exactly what's missing.
So this is the representation that they are presenting. So I'm just wondering, it's similar but not the same. But you know.
Oh, that's right. Hang on, I just go to here, and then is it this one? Yeah. Okay. Great. So I'm gonna go here.
Because now there is also the same version of this library in TypeScript.
Right,
so
if you
it's
go,
like easy accessible.
Sure, I understand. Go to GitHub and look up the Lighthouse repositories. So Leithaus.
Oh, I have your. Okay.
All right. So you want to screen share so I can see?
Oh yeah, sure.
Okay. So you want to go to papers and or maybe presentations. No, presentation. That's weird. Hang on. Scroll down for a second. Let me just see. It should be. Oh, talks. That's it. Talks. Okay. So if you look at, here we go. So start with the discrete graph. Okay, now look at the code necessary to build a discrete graph. It's a one-line equation. Discrete of n is equal to v dot 0 plus discrete of n minus 1. That's a one-line piece of code, right?
Mm-hmm.
Okay, now go back and look at chain. And chain of n is equal to let u equal x in E of let x equal v in discrete of 1, chain of n minus 1. It's a one-line piece of code, yes?
Yes.
Okay, great. Now go back. Now look at cycle. And just note that it's a one-line piece of code.
Yes.
Okay, now go back to complete. Note that it's a one-line piece of code. So what this says is that despite the fact that the complexity of the graph is growing exponentially, the code to represent the graph is remaining relatively constant.
Yes.
So try the same exercise with your other graph libraries and see what happens. That's the essential critique. Now, it also turns out that I can see a lot of things at the type level about graphs. So if you go back and then look at the graph algebra. So where is it? There you go. So there's the algebra. And there are all kinds of interesting things. Because we have these explicit representations of graphs, like we know how to form a graph from other graphs as opposed to adding a vertex to a graph. I can do things like pick out a subgraph of a graph, right? I can say, I'm just gonna assign X to be some graph and then use X in the formation of a new graph, right? So I can, for example, I could iterate, a graph side by side just as an example. So because I've kind of turned things on its head a little bit syntactically, right? Like finding a subgraph inside a graph has really bad complexity, but setting X to be a particular subgraph that I have in my hand in a construction of a new graph, well, that has no complexity at all. I mean, I already have the graph in my hand, so I don't have to go find it, right? So it flips things around. So I'm avoiding all kinds of complexity issues like subgraph isomorphism, which is known to be NP complete, right? So I can see things at the type level that other systems can't see. And when I'm building graphs, the complexity of the code that builds the graphs does not grow as fast as the graphs does. Complexity. Yeah.
And you are using for edges. I mean,
There are
this
two.
looks like
there's anonymous edges and there are named edges.
Oh, and
so the name of the edge is just the pair in the anonymous edges. But if you give the edge a name, you say E. Now, what you have to do is you have to pick out a vertex in your graph. So you say let X be the vertex V1 in G1, and you let X2 be the vertex V2 in G2. So you've named the two vertices in these two graphs that you're going to connect, and then the edge represents the connection between the two vertices.
and this looks like binding some name. Like,
yes, that's right. You're binding X to a vertex, X1 to a vertex, and you're binding X2 to a vertex. That's exactly right.
And this is a little strange to think about graphs in this way.
It's different. It's very different, and it's exactly this difference, being able to name a vertex that is the essence of my construction.
Yeah, I mean, essentially, you're memoizing the subgraphs where relevant, so that you can identify things of interest. Is that what's going on?
Well, that's the subgraph construction. In the vertex construction, I'm just naming vertices as opposed to entire subgraphs. So if you look up here, I have a type that is specifically about naming vertices in graphs.
Mm-hmm.
Right? And this generalizes to the comprehension where I pick out the vertices in G that satisfy a condition. Right? So these two things are correlated. This is the single version, and this is the generalized version. Right?
Right, but I mean, by having like named and anonymous vertices, I mean, is the practical implication that you have to name only things that might be of interest, and let others be anonymous or dynamic, or what's the?
No. The practical implication is that the only way to form an edge is by having a vertex in your hand, and the only way to have a vertex in your hand is to bind it to a variable.
I see.
And we can create more structure for the name itself, for the name of the edge, and maybe pattern match on this, or
yeah, you can do that. I don't do that, but yeah, you can do that.
okay.
Right.
And
So the other point is that because these things are because these are dependencies in your type for graphs, right? So the variables are dependencies and vertexes are dependencies. Edges are not dependencies unless you include the names, right? But if we're just using anonymous edges for purposes of discussion, then again you have variables and you have vertices, and so now you can play reflective games. And that's what toggle is all about.
so variables are somehow they're not real edges. We are just
a variable is literally just used to name vertices in a graph, and then you have a separate set of variables which are used to name entire graphs.
I see.
So a graph, the type of graphs G is dependent upon some set which you're going to use for your variables and some set which you're going to use for your vertices. And if you want to get like more complicated, then you also have another set of variables for mentioning subgraphs. So you would have G of of X, G of curly X, and G of V. So variables for vertices, variables for graphs, variables for variables for vertices, variables for graphs, and vertices themselves. Those are your dependencies for the type G. Those are your arguments for the type G. Does that make sense?
Yes. Now I have much more information to somehow compare, and because they're not talking about variables at all. And I know that you said just by working with vertices and edges is not exactly the point.
Yeah, that's exactly. So again, what I was trying to do was to keep. So if you've ever worked with actual graph libraries like Dot, right? Then or Graphel or any of those things, you discover quickly that as the complexity of the graph grows, the data representation grows equivalent, like basically linearly. And since we know that most graphs that we're interested in are algorithmically generated, we're not interested in, like arbitrary graphs. We want graphs that come from, they're generated by some program. So I want to characterize the algorithmic nature of the graph. Does that make sense?
Yes.
So it's like build a data type that manifests that, and then it will have this nice property. Like it's like I built it in that way, and then I tested it to see, okay, how does the complexity of the expression that builds the graph change as I change the complexity of the graph? And what I showed was, you can see it for yourself, right? As the complexity goes higher and higher and higher, the expression that represents it remains more or less constant. They're all one-liners.
So I wonder if you could use this to create like a new version of a GraphQL that is more useful, or is the abstraction that GraphQL is operating at too simple to make a difference?
No, that is exactly the point, right? Is that once you have the type theoretic view like this, then turning it into a query language is a no-brainer, right? It's like the whole point of OSLF is that the relationship between types and queries is an isomorphism, right? It's like every type gives you a notion of query, right? Here, let me have the screen back. Okay, so the notion of query is again, it's for pattern from source where condition, and then yield result. Of whatever the variables are bound by pattern, right? So source is giving you, pattern is giving you the query language that is generated from the type constructors. Your pattern matchers come from your type constructors. So source has got to be, basically something that contains things that are only built from those type constructors. The pattern matchers tear down the things on the basis of their structure, and then there are potentially some conditions which are not expressible in terms of the deconstruction, and so you want to capture those, right? So this is exactly select from where, right? If I just change the for expression to select, right? Select select results from source where condition holds, right? So this is exactly select from where, and the pattern matching capability comes from the term constructors, which are the type constructors, right? And then you have an additional set of conditions that have to do with mostly have to do with some equations that have to hold over your base types, but might also have to hold over your types in general. So these conditions come from the equational characteristics that were imported from your base types, and that's it, right? So once you have your data type, you know how to generate your queries. So when I was talking in the fall about all these query language constructions, this is the algorithmic way to generate that. You give me your data type, I can now tell you what the pattern matchers are. And in general, I can tell you what your conditional language is. And that's how I get queries. Notice that is exactly what happens with the tuple space and Rolang. So the tuple space is, a database over which we can pattern match, right? And whatever values we put in the tuple space, right, that those values, is assuming they follow a type discipline, we can pull them apart. So if the only thing for example, if the only thing we ever stored was Rolang terms, well, we know all the term constructors for Rolang, so we know how to pull them apart using patterns. And so then I can express a query language over those. If I enrich Rolang with some set of base types, like the natural numbers, the Booleans, lists, and things like that, then all of those additional term constructors become pattern matchers that, again, I can use in the formulation. And this is entirely algorithmic, right? Generating the query mechanism from the type descriptions is entirely algorithmic. So I use that very same algorithm on the graph algebra that we were looking at just a minute ago. Does that answer the question?
Yeah. Thank you.
Thanks for the question. All right. Well, thank you so much. It's 8 o'clock. I'll see some of you in the Dev Stand-Up.
Thanks.
Thank you.
Thank you.